Okay, let's get started. Welcome to our 7th lecture. Let me get rid of this floating meeting controls here. Okay, now that we've covered combinational and sequential logic, and we built everything from the transistor as a switch up, we're going to talk about how to describe what we have covered, basically how to describe logic in general. And we're going to introduce the notion of hardware description languages. This is going to be similar to other software programming languages, except they have two major differences. They're going to be specialized for hardware, and they're going to be extremely good at parallelism and concurrency, as we will see, and as you will find out in your labs as we go forward. This is, in my opinion, a relatively easy lecture. It's about programming, and you've already had programming languages, right? In your class, yes, but you haven't seen hardware description languages. How many people have used hardware description languages before? Okay, a small number of people. You're in the minority. How many people have used Verilog before? Okay, wow. Where did you use it? I'm curious. Oh, okay, in this class last year. Okay, sure, yeah. How many people who haven't taken this class ever have used a programming language, a hardware description language? Okay, where did you use it? Okay, you did. Okay, so it's really related to this class somehow. Okay, well, that's what I expected basically. If you have not exposed to this class, probably you have not used hardware description languages. But it's important to learn, and it's really critical to design hardware. It's fun also. Okay, so let's get started. These are just general reminders. These are readings. I don't want to harp on. Next week, we're going to cover the von Neumann model, ISA, and programming, higher level programming. Today, we're going to cover the hardware level programming, let's say. And remember that you have extra credit assignments that you can do if you wish to get additional credit. Okay, today's agenda is we're going to talk about what I just said, and we're going to look at implementing combination logic as well as sequential logic, specifically in one of the major hardware description languages called Verilog. And the Verilog slides really constitute a tutorial. So we probably are not going to cover all of them in a lot of detail. And some of them we're not going to be able to cover at all, especially at the end of the lecture. But it's good for you to look at them. And certainly they'll be beneficial for your labs. So if you're going to do the labs, then you will see that these Verilog constructs will be very useful. And we will soon see something called an LC3 processor, just to jog your memory. Whenever you implement a processor, it has sequential components and combinational components. And I wanted to show you over here, there's a finite state machine over here that controls the execution of instructions in this processor. We're going to look at this processor partially, but this is not what you're going to implement. What you're going to implement is much simpler than this, even though it's a very simple processor. This is called little computer. But I'm going to give you examples of how instructions execute, controlled by a finite state machine through a data path that's mainly combinational, but also have sequential elements like the register file and some registers like instruction register, program counter, etc. So this is what will come next week and the week after that. And you will see how this thing operates, how we will use combinational and sequential logic to actually design a very, very simple microprocessor. Does this sound like fun? Basically, you'll design something that works hopefully in the labs. But to be able to do that, you need to be able to specify what you will design. And that's where hardware description language actually come in. Just to motivate you, why is this important? I mean, why not? Why do we actually design a language? Why do we program the hardware using this language? Why not basically draw schematics of AND and NAND and NOR gates and declare victory? Well, the reason is it's too complicated to do that, basically. You need a level of abstraction. Remember the level of abstraction, the transformation hierarchy levels? You want to hide the details of the lower level so that you can effectively design a chip that may look like this, for example. Because if you look at this chip, this is 4 years old by now, 5 years old by now, actually. It was the state of the art 5 years ago. And you can see that it's complicated. You will understand what pipeline means, what threads mean, etc. later in the course. We'll talk about clock. We talked about clock in the last lecture. You can see that this is almost 4 gigahertz clock frequency, which is quite high, meaning state changes happen at the frequency of 4 gigahertz every 2.5. Now I'm going to make a mistake, right? Every 0.25 nanoseconds, basically. And there are 1.75 billion transistors. And You can basically guess how many gates there are. It's on the order of hundreds of millions, right? And designing this at the gate level is a huge problem, basically. It will take you a long time. That's why we need abstraction. And that abstraction comes as hardware description languages. And this is not getting better, as you can see. This is not the state of the art, of course. We will see that also. And transistors are growing, and the complexity of the chips are also growing. This is what you have seen earlier. You can see that this is 4 years later, and the number of transistors have almost increased by 10x, 8x or so. And more recently, we've seen this also a couple of weeks ago, right? And the number of transistors has increased compared to the previous year, let's say, by 7x or so. Now, granted that this is actually a bigger chip, so the transistor density has not increased, but the number of transistors is increasing, which means that complexities has still increased in this design. And we also see in other designs where complexity is also increasing, 1.2 trillion transistors, 2.6 trillion transistors. If you had to actually implement everything gate by gate, you will have a big problem. That's why we have a hardware description language. We want to deal with the complexity. And again, these are very complex chips, right? They're going to get even more complex. Even 10 years ago or 15 years ago, things were complex. And even earlier, things were complex because designing things just at the gate level is just not productive. Okay, so that's where hardware description languages come in. And the question is, of course, what do these provide? So what do we need for hardware design, in other words? There are three things, basically. We would like to have the ability to specify the hardware, specify the complex design, how it operates. That's one thing. We're going to look at that for sure. We'd like to have the ability to simulate the behavior of the thing we specified in terms of both functional behavior, like we have seen so far, and the timing behavior. And this is important to make sure that what you have specified actually works according to the specification, right? That's where simulation comes in. And we're going to talk about that also. You'll do a lot of that in your labs to verify your circuits. And then also, we would like to have the ability to automatically synthesize, in other words, automatically design portions of it or all of it. So imagine if you specify some hardware using a description language and put it through a translator and compiler, and the compiler gives you the exact gate level implementation. That sounds great, right? Then as a hardware designer, your job is very simple. Just write the program at the language level. And today, actually, tools are quite good to be able to do that, but not good enough to actually meet some of the really stringent requirements in terms of performance, power, area, and thermals, for example. So today, we can partially do this, or mostly do this, but not at the critical parts of the circuit. But going forward, this will become more and more, hopefully better in the future. So this sounds very powerful, right? You write your hardware description in a higher level language, and that enables you to specify, simulate, and synthesize. And these are the three major goals. Well, why synthesis, you can say, right? Synthesis is interesting. Why not actually design, again, everything by yourself? Synthesis, enabling automatic design is good because it can get rid of errors in your implementation. When you design something by hand, even if you're using a hardware description language to go ahead and implement it later on, you may have errors. Whereas if you actually have a compiler that does that for you, goes from hardware description to logic gates and eventually the hardware, then this could be error-free because you may actually verify the compiler and make sure it works perfectly. You may prove that it's correct, right? That's also another area that's a tough area, but you can gain a lot of confidence in your compiler. Okay, so that's why synthesis is important. So keep in mind that whatever we're going to discuss today can be synthesized automatically into hardware logic gates. And HDL, in short, hardware description language, enable all of these above. What are these basically? These are languages that are designed specifically to describe and specify hardware. And they're similarly featured HDLs. We're going to focus a lot on Verilog today. There's also VHDL. I have another slide that talks about this. They're very similar, basically. Their syntax is different. They have some idiosyncrasies. None of them are perfect. But if you learn one, it's not hard to learn another. There are also some other languages. Some of them are at similar level of abstraction. Some of them are at higher levels of abstraction than these two languages, but we're not going to cover them. And clearly, mapping between these languages is typically mechanical, especially for the commonly used subsets. Basically, it's a syntactic mapping. You can map from Verilog to VHDL and VHDL to Verilog. I mean, similarly to other programming languages that you may use, right? You can map from Java to C++. If you know Java, you can easily learn C++. If you learn Python, you can even more easily learn Python, for example, if you learn Java. And if you learn C, you can easily learn other languages because C is at a much lower level of abstraction in general. So once you learn a programming language, learning another programming language is not that hard. So it's similar over here. So in a sense, this is essentially a programming language, but it's a special programming language. And we'll talk about why we need special programming languages in a little bit. But before that, I will quickly mention that there are two well-known hardware description languages, Verilog and VHDL. And these are commonly used in industry. In fact, I'll just go through it quickly. In fact, basically, these are not that important in the end. These are historical, basically. The reason there are two are historical, and one of them is more popular in the US, one of them is more popular in Europe. Don't ask me why. Again, it's historical. But these languages are really commonly used in industry today. Industry, what they do when they do hardware design, and today, almost all companies that are working at the cutting edge are doing hardware design, as we discussed, right? Even people who are designing cars, car companies are doing hardware design. So they usually use a variant of this language. They may actually change the language so that it can specify their needs. Usually they don't develop something from scratch, although it's possible to develop something from scratch as well, right? So in this course, we will use Verilog. I personally like Verilog better, but that's a personal choice in the end. But let's talk about something more fundamental. Why do we need specialized languages for hardware? Why not Python? Why not take Python and basically say, in Python, I write my circuit. I specify it somehow. You can do that. Why not? And then use it to somehow use Python to synthesize as well as simulate. Well, because it's not easy if you want to do that. It's not easy to do certain things, especially description of hardware structures is not easy. It's possible, but not easy. The constructs you have in the language don't map nicely to the constructs that you have in hardware, for example, and or not gates. You certainly have those, but as we will see, there are more things that you need. Wires, gates, registers, flip-flops, clock, rising and falling gates. We will see that these hardware description languages actually have that inherently in their design. You could say that, okay, I can write a Python library, and yes, then now you're specializing the Python toward hardware description. You can basically create Python hardware description language, potentially. So it's possible. And certainly we will see combinational and sequential logic elements that are they're also inherently supported in the language as we will go through this lecture. So the second thing that's even harder in existing software languages like Python or Java or C++ or C, even though C is at the very low levels of the stack, is a seamless expression of parallelism. If you look at hardware, it's extremely parallel. If you look at a chip that I showed you earlier, everything happens concurrently. Clock goes everywhere, and all of the logic evaluates concurrently. In fact, if you really understand how to build hardware, you should really more easily understand how to build concurrent and parallel software. And this does not get expressed in existing languages very well. So existing languages, if you look at C, for example, or Java, or any sequential language, it's sequential, right? One statement is executed after another statement executed after the previous one. It's very sequential. But hardware is completely different. You need to really think about parallelism when you design hardware. And in fact, if you get a knack of this in this course, then I believe you will be a much better software engineer and a parallel programmer, because you really need to get used to parallelism that exists in hardware. And in general, actually, very good hardware designers that are experts at these languages and designing hardware are also extremely good parallel programmers. At least in my experience, I've seen this many, many times. So these are the two major reasons why we need specialized languages, because existing languages don't easily express hardware structures, although it's possible to extend them for this. And existing languages really are terrible, let's say, at this inherent parallelism, and they cannot express that. And both of the above really ease specification, simulation, and synthesis. So if you do both of these, then specification is easy. Simulation is easy. Existing languages also don't have support for hardware simulation. We will see that, especially tomorrow. And synthesis is also much easier if you start with, for example, a description of hardware structures. If you start at a very higher level of abstraction, it may be very difficult to automatically synthesize, because of search space to map that higher level of abstraction to gates and bits and logic and different components is much harder for a compiler that would compile from, for example, Python into the gates. It's possible, again. You can imagine building a Python compiler that compiles it directly into the gates, not into the instructions of the instruction set architecture. It's possible, but it's not efficient. And what you get in the end may not be as efficient as what a hardware description language will enable. So we will talk about this also later in this lecture. Okay, does this make sense? Okay. Okay, let's move on. So now let's go into how we can do hardware design using description languages. Basically, the key principle is very similar to software, hierarchical design, right? You really have a lot of complexity, and you want to use hierarchy to tame that complexity. I'll put this over here. And this is one example over here. Basically, we want to design a hierarchy of modules. And you can see that there's some hierarchy over here. Even within a cache component, there's a hierarchy. And in the end, the hierarchy ends with gates over here. We have some predefined primitive gates, and or. You will see that in the language. We built simple modules by instantiating these gates. For example, we build muxes using by instantiating these gates, like we did in the previous lectures. But we're going to do it in a language today. We can build complex modules by instantiating simple modules, as well as primitive gates. So that's how you build hierarchy. And hierarchy really controls complexity in the end, because this is very similar to using functions in your programming, right? If you're doing software programming, if you don't use any functions, it looks like a mess, right? Especially if you're doing a huge project. But clearly, functions and other productivity techniques help that. And complexity is a huge problem. I don't want to motivate this again, but clearly we're dealing with billions of transistors today. If you have to specify every single gate, then you have a huge problem. If you have a hierarchy, then you basically raise the abstraction level, and you basically say, okay, this is my cache module. Underneath, maybe I don't care how it's implemented, because I already implemented it once, or somebody implemented it in a great way. I take it, and I'm going to use it in my processor. This is my cache. I'm going to instantiate it, and we will see that. That way, you basically get rid of a lot of complexity. Okay, so to use hierarchical design, there are two kinds of methodologies. One is top-down, one is bottom-up. Again, this is very similar to software engineering, since at some point we're doing software engineering also here to describe hardware. Basically, in a top-down design methodology, you design this top-level module first, and then identify what sub-modules you need to build the top-level module. For example, if you're designing a memory, like we have discussed in the prior lecture, you need a decoder, you need a multiplexer, and you need D flip-flops to actually have the memory array, right? So top-level modules, memory. Sub-level modules, maybe the decoder, multiplexers, and the D flip-flops, right? You could also divide in some other way, of course, right? And then each sub-level module, a sub-module actually, you basically keep doing this repeatedly until you get to leaf cells. So what's a leaf cell? Leaf cells are circuit components that cannot be further divided. So this could be very basic logic gates, like AND gates, NAND gates, NOR gates. Or it could be primitive cell library elements. So it depends on your goal. Your goal may be to design design into some library, let's say. This is a library that's library of hardware modules that you want to use in your design. And somebody create a nice library, for example, a nice multiplexer, a nice cache, and basically say, this is my lowest level module, leaf cell. A nice cache is my leaf cell. A nice multiplexer is my leaf cell. And maybe AND or NOT gates also exist over there. And your goal is to basically express the submodules hierarchically, and in the end, in terms of leaf cells. Does that make sense? Okay. So basically, your hardware description eventually ends at these leaf cells. But remember that leaf cells can be at different levels of abstraction also, if the library provides that abstraction. In fact, it's very nice to have that abstraction. Somebody designed this beautiful multiplexer, 8-to-1 multiplexer. I don't care how it's implemented. That's my leaf cell. If I'm going to use that in a submodule, I'm going to just instantiate that leaf cell. I'm not going to go into the AND or NOT gates that implement that leaf cell. Okay, that again tames complexity. You can also do this bottom up. You first identify what are the building blocks that are available to us, or build those building blocks to begin with, and then build bigger modules using these building blocks, and then figure out how to combine these submodules so that you can get to the top level module. Both ways are actually possible. They can be equivalent. Usually, both ways are used. For example, when you build a library, you build a library of leaf cells. And then when you want to build a processor, a component of a processor, you do the top-down design going into the leaf cells. And then you may figure out that a leaf cell is missing, right? Then you build more leaf cells. Okay. So hopefully this is clear, right? I'll go through some of these relatively quickly because some of these are relatively obvious also. Let's take a look at our first definitions of Verilog. So basically, a module is the main building block in Verilog. Everything's a module in the end. And you first need to define the name of the module when you actually write it. That's an example, as you can see. And you need to define the directions of its ports. inputs or outputs. Those are the two directions. Simple. We've seen that. And you need to assign names to the ports. So now you can see that this could be a circuit, right? This is an example circuit. It could be combinational or sequential. We'll see both later on. And then describe the functionality of the module. So the functionality is what goes into the code, in addition to these three definitions over here. So let's take a look at an example functionality that we implement in this module. So this is one over here. You can see every module looks like this. You can specify inputs and outputs this way. And you need to name the module. The circuit description comes here. And we're going to see many examples of circuit description in this course. And then you need to end with end module. Okay, I think these are obvious, so I'll go through this relatively quickly. And the following two codes are actually functionally identical. Verilog allows you to do both. You can actually declare the inputs and outputs whenever you actually in these parentheses, in the function parentheses, or inside the function, the first thing over here. Okay. Basically, here you really combine the port name and the direction. Of course, this is a question of style and consistency. It's always good to have a consistent way of designing things whenever you're doing any design, software or hardware. And this may be dictated by somebody who defined the style. And it's good to always have a good style, basically. Okay, I'm not going to go into the style issues in this particular lecture as much. So what if you have multi-bit input and output? Again, you can define multi-bit input and output. This is called a bus. This bus is essentially a set of wires that operate concurrently. And you basically specify it this way. This is the range end and range start, and there are two numbers over here. Let's take a look at examples. A number of bits inside the input or output wires are the range end minus range start plus 1. For example, this A is now a 32-bit input. This B1 is now as 8-bit output. This B2 is also an 8-bit output. You can specify it as you like. And there's a single signal, single wire, basically, single-bit input. Okay, I already said this, I think. And usually there are actually two ways. Verilog allows you to do things in different ways. This is a better way, in my opinion. This, in my opinion, should have been perhaps forbidden because this resembles an array definition in Verilog also, which you will see later on. So it's in general good practice to be consistent with the representation of the multi-bit signal. So it's better to, in my opinion, use this one. Use this one over here as opposed to this one. Okay. So let's talk about manipulating bits. So this is also called bit slicing. Basically, we'll see concatenation. This is an example of concatenation. So if you have one wire, Y you can see in this case is 4 bits. And you can concatenate, you can form this 4-bit wire by concatenating these 4 bits. Second bit of A, first bit of A, 0th bit of A, and 0th bit of A. These are least significant bits of A. And this is, I guess, first and second bit. So you're basically taking it from somewhere. And then if you want to duplicate, you have this assign. For example, if you want to create a 4-bit wire out of 1 bit, A0, 1 bit, you want to duplicate that 4 times. This is how you can do it, essentially by concatenation. And this is another way of doing it. These two are actually identical, equivalent. So there are multiple ways of expressing things. Hopefully these are simple syntactic issues. You will see, you'll use these a lot in your labs. So Verilog is case sensitive. So these are different things in Verilog. That's the choice the language designers made. Names cannot start with numbers. Again, white space are ignored. So hopefully these are obvious. And you will really get to know these once you actually go over things. Let's talk about something more substantial other than syntax. So syntax is important, of course, when you're programming. You need to obey the syntax, otherwise you get a syntax error, right? But let's talk about something conceptual. This is really important because it will have implications on how we write Verilog. So there are two main styles of hardware description language implementation. One is structural, gate level. That's the definition, basically. Everything is specified at gates or modules that are built on top of gates. In this case, the module body contains gate level description of the circuit. And once you define a module, you can actually connect the modules, of course, but modules are gate level. You describe how the modules are interconnected, and each module contains other modules, instances, as we will see soon. And interconnections between those modules as well. So basically, we will interconnect these modules. Okay, so this describes a hierarchy of modules defined as gates. So this is one way of defining hierarchy. But this is very low level, meaning you really need to specify a module using gates. Behavioral, on the other hand, is much more abstract. The module body describes a functional description of the circuit, and this can be at an abstract level, as we will see. It's best seen via examples. You can here, for example, you can contain logical and mathematical operators, expressions. You can have a while loop, for example. So there are interesting things over here. So the level of abstraction is higher than the gate level. So you don't need to specify everything as gates. This is more like a higher level programming language way of defining how hardware operates. And if you actually look at this, because of this high level of abstraction, there are many possible gate level realizations of the same behavioral description. You may have one behavioral description and it may lead to thousands of different gate level realizations. Whereas a gate level structural Verilog, it leads to one. Unless, of course, someone is smart and they optimize the circuit, that gate level circuit. But still, the options are limited over here. Whereas in terms of behavioral, you enable many, many options. So from that perspective, behavioral opens up a lot of possibilities for tools, but it may also make it difficult for the tools to actually find an optimal solution or a solution that the user really desires, for example. So in the end, many practical designs actually use a combination of structural and behavioral Verilog. Okay, we'll see examples of this. So if you don't understand exactly how this works, you will soon. So let's talk about structural or gate level HDL. So this is one example. I didn't define the module over here, but let's take a look at how we instantiate modules. So assume that this is the top level module that we want. And it consists of two small modules that are identical, ABY, and they're both small, as you can see. And they're interconnected like this to the inputs and to each other. You can basically start with a schematic. A schematic is essentially a pictorial representation of your circuit. This schematic of module top is built from two instances of module small, simple. You'll build a lot more complicated things in this course. This is how you define things, basically. This is the module definition of the top module. It has three inputs, A, select, C, and then one output Y. And there's a wire. The connection is defined as a wire, as you can see, N1. Okay, and then clearly the naming needs to be there. Okay, and then you first instantiate the small module one. So okay, I didn't talk about small module, but it's the same basically. The name is small and it has two inputs, one output. And then there's some description which we're ignoring right now. It could be a mux, for example, multiplexer, but ignore that for now. This is how you instantiate the module basically. This is the first module. You can name it I first, as you can see over here. And then you basically tie the A input of the small module to the A input of the top module, B input of the small module to the select input of the top module, and the Y input of the small module to the N1 wire, which is output. So Y output of the small module to the N1 wire that's defined in the module. So basically, you need to map the inputs and outputs to parameters that are or wires inside this function. Let's say modules are like functions basically. But basically, you're connecting modules in this case. Okay, and the second one is also similar. Now, you can see that the A input is tied to N1, which is here. That's the input. B input is tied to C, which is the input from the higher level module, top level module. And then Y input is tied to Y output over here. Y output is tied to Y output over here. Okay, so hopefully this is simple, right? You're just defining modules. There are also simpler way. Basically, you can here we're explicitly specifying which inputs, input and output ports of the small module correspond to which parameters over here or wires over here. You don't have to do it explicitly. You can do it implicitly, but then you have to preserve the order. So here, just to show you, this is explicit. This one is implicit. You need to preserve the order. I mean, A needs to be A over here, select needs to be tied to B, and N1 needs to be tied to Y. If you mess up the order, then you have a problem. You may have a bug in your circuit, and these are actually bugs that may be very difficult to find and fix. It basically wastes your time in the end. So this is called the short form. Short form in general is not good practice as it reduces code maintainability and readability. Safer choice is always to do this, basically. Here you can use any pin order because you're explicitly specifying which pin, which input and output is tied to which parameter or wire over here. Make sense? Again, if you're consistent in everything, maybe you can use the short form also, but short form becomes very prone to bugs. Okay, the second example here is, another example of structural HDL is Verilog supports basic logic gates. These are called primitives, predefined primitives. You don't need to define them, basically. And these primitives are instantiated like modules, except you don't need a module definition. For example, this is a mux multiplexer. We've seen this multiple times so far. And it's a 2-to-1 mux. And 2-to-1 mux, you can write it using these basic primitive gates. So NOT is provided by Verilog, AND is provided by Verilog, OR is provided by Verilog. And basically, you can convince yourself that these two input, these gates are essentially correspond to the schematic over here. Of course, there's some assumption over here. The leftmost output, the leftmost parameter into the module is the output. And that's the case, actually. Does that make sense? So there's some ordering that's essentially implied in this by Verilog. So you need to get used to that ordering. Okay, so that's one example where the language specializes for hardware, as you can see. You don't find NOT, AND, and OR modules in existing programming languages. Okay, well, software programming languages, not hardware programming languages. Okay, let's talk about behavioral so that we can see the difference. Okay, I already said this, so I'll go through this relatively quick. But just to remind you, behavioral, here we have a functional description. It doesn't need to consist of gates, essentially. Level of abstraction can be higher. As high as possible, you can go. This is not very high level of abstraction, but this is still not gates, as you can see, right? Here, I don't have an AND gate, NOT gate, OR gate, nothing. I basically assign Y to this Boolean equation, right? And we'll talk about precedence also. The NOT gets precedent over AND, which gets precedent over OR. So it's basically this or this or this. So you can see that this is behavioral. I don't know what gates these may be. I can implement them using clearly AND and OR gates as well as NOT gates, but I never said AND or NOT over here. It's purely Boolean. Okay, and this is a behavioral implementation still models a hardware circuit. Don't get confused, basically. Structural, behavioral, it's still models a hardware circuit, except the circuit may not be exactly how it's described in the behavioral case, because behavioral may have many, many possible implementations. And this is one implementation of what is described behaviorally over here. So we will see other descriptions soon. So you can have bitwise operators in behavioral Verilog. This is bitwise AND, bitwise OR, bitwise XOR, NAND, NOR. These are basic gates that you have seen, except they're not gates here. They're behavioral bitwise operators, just like you have in other languages, or at least many other languages. And this is a schematic view of what we just looked at over here. I'll go through this relatively quickly because you will do this when you're programming. The best way of learning a language is really by doing programming using that language. Okay, so you can have reduction operators in behavioral Verilog. So this is an example. You assign Y to a bitwise AND of all bits in the wire or bus A. So A is an 8-bit input in this particular case, and Y is the bitwise AND of all of the bits in A. So it's much easier than writing this basically. So Verilog allows you to do these kind of tricks. Once you get used to it, actually, you'll use these tricks and it's fun. And that's basically an 8-input AND gate, right? But again, this may not be the realization, circuit level realization. So going back, this is the behavioral description. It says, I have an 8-input AND, but underlying implementation may not be like this. Underlying implementation may be a tree of multiple AND gates, right? Because you may have only 2-input AND gates in your library, for example, or only 4-input, 3-input, and 2-input AND gates, and you may not have an 8-input AND gate because of the reasons we discussed when we talked about basic logic gates, right? Because once you have an 8-input AND gate, you have a very long sequence in the serial transistors, and that may actually increase the delay of that AND gate. That's one implementation of the AND gate. Okay, does this make sense? I see some nods. Okay, good. Okay, again, you will get used to it. It's always kind of odd, in my opinion, to describe a programming language and how it works, because in the end, you're going to write code in it, and you're going to learn it much better by writing code, in my opinion. Okay, conditional assignments. Again, this is not behavioral. This is a mux described conditionally. It's a 4-input. It's a 2-input 2-to-1 mux, but each input is 4 bits, except for the select, of course, because select is dependent on how whether the m value in the n-to-1 mux. Basically, you use this conditional or ternary operator. This says that y is equal to check x. If s is 1, then y is equal to d1. If s is 0, then y equals to d0. That's essentially a multiplexing operation, right? And it's beautiful that we can describe it this way. We don't have to describe a multiplexer using gates here. This is behavioral. The gate level implementation, I don't care. eventually this gets synthesized, and hopefully somebody does a good job with that synthesis so that I get a good gate level implementation. What I care about is the functional description. And this is very functional, as you can see. Right? There's no gate specified over here again. There may be many, many implementations of this mux. It could be a lookup table, as we have discussed in the past, right? Okay, this is one potential. Well, this is a schematic view. And again, this doesn't go into the gate level, as you can see. This is the mux module view. Okay, you can do more complex conditional assignments. Again, it's a 4-to-1 mux, as you can see, mux 4. It's cumbersome, as you can see. You look at bits. S1, this is a 2-bit select input. Clearly, when you have 4-to-1 mux, you have a 2-bit select input. Remember that. Basically, you're basically selecting hierarchically over here. You look at bit 0 first, and then bit 1 next, and then select the outputs. And this is another way of writing the same thing, using looking at 2 bits at the same time. This is potentially a higher level of abstraction, right? Basically, Y is assigned to D3 if the select input is 1, 1. Y is assigned to D2 if the select input is 1, 0. Y is assigned to D1 if the selected input is 0, 1. Otherwise, Y is assigned to D0. Clearly, this is, in my opinion, easier to understand and read than this hierarchical view. But there are multiple ways in behavioral Verilog. Okay, and then you can find out other ways, which I'm not going to go into. Does this make sense? Again, this says nothing about gates. This can be implemented many, 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 many ways. Okay, so I've already mentioned this before, but there's a precedence of operations in Verilog. Not gets the highest priority. Ternary operator is the lowest priority, so that you can do a lot of things inside that ternary operator. And there's a prioritization level. You don't have to rely on this. You can always add additional parentheses to make sure that basically everything in parentheses is executed first, right? And then you go into the outer parentheses. But you can also, if you keep adding parentheses, it's actually additional overhead and makes readability hard. So there's a sweet spot between relying on this precedence versus relying on parentheses. But again, this is true in many other languages as well. How to express numbers, some more basics very quickly. This is one way of expressing an 8-bit value, for example. Usually any number is expressed this way. N specifies the number of bits. I already said this. B specifies the base. In this case, it's binary, as you can see. And you can see there are multiple others that are supported in Verilog. And this is the number, obviously, right? Hopefully this is obvious. And we already seen examples, actually. You can also have invalid and floating values as values. We've already seen these, actually. I will briefly go over this. And underscore can be used to improve readability, as you can see over here. So underscore basically separates a cluster of digits from others. This is just for readability. It doesn't have any meaning in terms of the specification of the number. Okay, you can see some examples over here, right? I don't know what's interesting over here. You can study this on your own. Okay, floating signals. Remember, this is something, and you have to study this on your own anyway when you do the labs. Okay, floating signal is a signal. Remember, this is a slide that we saw before, actually. This is a signal that's not driven by any circuits, right? And we've seen this when we talked about tri-state buffers, for example. Open circuit or floating wire. This is also known as high impedance or high Z or tri-stated signals. And you can see one example implementation of a tri-state buffer, right? So this is a tri-state buffer. Input is 4 bits, output is 4 bits, and then it says enable signal. If enable is true, output is assigned to A. Otherwise, the output is floating. And this is how we express floating. Basically, the tri-state buffer doesn't let any value go through it if enable is 0. And we've seen this. Just to jog your memory, okay, if my computer allows me, you can see that this is what we have seen in the combinational logic lecture 2. And you can see that this is essentially the same functionality as we saw. It's behavioral over here. And we've also defined what a floating signal is at that time. So just to jog your memory. And remember again, a tri-state buffer acts like a switch. If the enable is enabled, the circuit is connected. If the enable is disabled, meaning it's 0, then the circuit is open. Okay. And again, I don't know what's going on here. Okay. I've also mentioned this during when we introduced tri-state buffers. Imagine a wire connecting the CPU and memory, and only one of them can drive a bus or wire. Then basically use tri-state buffers. And we will see this actually when we talk about the LC3 data path soon that I showed you, kind of flashed at you earlier. So only one of them can put a value onto the shared bus. And if, for example, if you want to put a value from the CPU, you set the enable here to 1, and you set the gate mem to 0. Okay, and from your book, something went quite fast. Okay, from your book, this is another example. You can find this example in your book. And this exists in existing systems. Existing systems are actually even more complicated because there is a shared bus that's shared across many devices, memory, processors, accelerators, etc. And whenever they need to communicate with each other, one of them puts a value onto the shared bus, and the other one receives a value from that shared bus, if there's a receiving end, of course. And you need to ensure that the control signals of these tri-state buffers are correctly set. And there's a logic that ensures that. That's called the arbitration or bus arbitration logic. You may see this later on, actually. And that's so basically, you may ask the question, who generates these enable signals? Well, there's another logic that's not shown here that controls. And that's based on something that we have kind of seen actually also, which is the priority circuit that I'm going to show next. Basically, there could be a priority circuit that takes the request signals from processor, video, Ethernet, and memory, and decides the enable signals based on the priority assigned to these different things. But before we go into the priority circuit, and I remind you again, the priority circuit, this is a truth table for an AND gate with Z and X. Z is floating. X is invalid in this particular case. It's not don't care, really. I mean, you can imagine don't care is kind of invalid also, but okay. But basically, you can see that this is really the end we are used to. Values are 0 and 1, input values. If one of the values is Z or X, if another value is 0, then the AND gate makes sure the output is 0. So that's fine. In all other cases where if one of the values is Z or X, then the result is undefined, basically invalid. Because it doesn't make sense to do an AND of a floating signal with another floating signal. The result is really undefined. You have no idea what the result would be. Invalid, basically. Okay, so remember the priority circuit I mentioned. This again, I'll go through this quickly because we covered this actually. You have requesters with priority levels and grant signal for each requester. And this was our priority circuit. We already know these X's actually there. In this case, they're don't cares. And this is our priority circuit that can control what we have seen earlier. Okay, any questions? I'm going through a lot of basics basically at this point. Okay, so what happens with HCL code? We kind of talked about this, but let's talk about it a little bit deeper. So there are two things that are important that happens with hardware description language code. One is hardware synthesis, or synthesis, short for short. So modern tools are able to map synthesizable hardware description language code into low-level cell libraries. So cell library we discussed is a library of gates and modules, and they take their this modern tool, can be called a compiler, compiles your code such that everything is instantiated to specify, to basically correctly implement your description in the code using using the modules and gates in the cell libraries. Makes sense, hopefully, right? And this is also called a netlist for historical reasons. Basically, this netlist describes what gates you use, what wires you use, and how they are connected with each other. Okay. So modern tools, for example, can take this, and then that netlist may get transferred to an FPGA as a bit stream, and then the FPGA may implement actually what you specified using hardware description language. And clearly, modern tools can perform many, many optimizations when they're going from the hardware description language to the cell library and the netlist, let's say. However, they cannot guarantee that a solution is optimal in general, especially with large circuits. If you have very large circuits, and if you have many requirements, timing, energy, area, performance, clock frequency, potentially, they may not be able to guarantee everything. They may actually not work in some cases because they're not able to consider many. This is a very multifaceted, multi-objective optimization problem, right? You have a huge circuit that you have specified, let's say, that needs to be mapped into some gates and cells, the functions in the cell library. And you have many goals. Timing should be like this, area should be like this, power should be like this, terminals should be like this, and they may not be able to satisfy this. So there's a lot of ongoing work in this area still to make these modern tools better. And again, the algorithms that are employed in these tools are fascinating, but they're out of the scope of what we're going to see. Just keep in mind that they're computationally expensive. So the placement and routing algorithms are very computationally expensive. So if you really want your circuit to be synthesized nicely, you need to describe your circuit in HDL in a nice synthesized way. And this is really the most common way of digital design these days. Most of the time, you don't implement the circuits yourself. For example, you don't take a cell level library and put together different gates and modules that you find in the cell level library. You go through a tool that compiles your hardware description language into that cell level library. But again, if your circuits, if the resulting circuit that comes out of this tool is not good enough, and you have high requirements, for example, you want to design the fastest ALU in the world and the tool is not good enough, then you actually need to go and implement things by hand. So there's a portion of digital design, which is a very large portion that's today automated. But there's some portion that's really important, smaller portion, that's essentially either semi-custom or full custom. If you may actually hear the semi-custom and full custom terms. What does this mean? Basically, you go and change things by hand, or by looking at it and actually changing the gates this way. Oh, I want to implement this gate as opposed to this gate, even though the tool implemented some other gate. Right? So there are portions of the design today where you have to do this because the tools are not good enough. Okay, but hopefully you're not going, well, you're going to do that in the lab somewhat to learn. So that's a good way of learning. So the second thing that happens with HDL code is simulation. And simulation is good. Here you don't actually design the hardware. The output of simulation is not the hardware itself. The output of synthesis is the hardware itself, right? You can map it to an FPGA, you can map it to ASIC, you can map it to a general purpose processor, but it's hardware in the end. Whereas simulation, the output is not hardware. You don't get any output other than, oh, here's a waveform, and here's how the circuit seems to work if I actually apply these inputs. Basically, this allows verification, allows the behavior of the circuit to be verified without actually manufacturing the circuit. This is very powerful. You have to do this. Otherwise, manufacturing the circuit is very expensive, right? You don't want to manufacture a circuit before simulating and verifying it. Okay, and simulators can work on both types of Verilog, or well, I say Verilog, but it's hardware description language, structural and behavioral. And this is really essential for functional and timing verification. We're going to talk about timing verification tomorrow. But even for functional verification, you want to see when these inputs change, what happened to input outputs. And if that change doesn't match your functional thinking about what you expect from the circuit, then there must be something wrong with your description in hardware. Or there's something wrong with the simulation tool, which is hopefully not the case, right? Hopefully simulation tools are verified and designed so that there's nothing wrong with the simulation tool. I mean, in synthesis also, again, there might be something wrong with your compiler, right? But hopefully, again, that's not the case. We're assuming those are not problematic. So let's look at this example. And then after this, I'm going to take a break after I talk about briefly hardware synthesis. So if you look at this example, this is behavioral, and this is synthesis. This is how it's synthesized. And this is how it's simulated. So you will actually deal with a lot of this in your labs. You can see the same example. This is the synthesis. This can be mapped directly into hardware. Or you can actually simulate it and look at a waveform diagram and convince yourself that things are working okay. Let me finish with this note on hardware synthesis, because this is important, and I'm going to read this directly from your book. And I agree with this actually, wholeheartedly. One of the most common mistakes for beginners is to think of HDL as a computer program rather than a shorthand for describing digital hardware. If you don't know approximately what hardware your HDL should synthesize into, you probably won't like what you get, especially if you have stringent requirements. I would add that. You might create far more hardware than is necessary, or you might write code that simulates correctly but cannot be implemented in hardware. So simulated doesn't mean that it can be implemented. So there's a difference between synthesizable and simulatable. And we will see that there's some simulatable code that cannot be synthesized. Instead, think of your system as blocks of combinational logic, registers, and finite state machines. That's the best way of thinking in hardware, actually. Sketch these blocks on paper and show how they are connected before you start writing code. And this is actually a very good advice, because sketching things is easy if you actually use hierarchical design principles also. Okay, any questions on this? Yes, please.
How do we know how our hardware is as a one-off hardware?
Say it again. How do you know how?
How can we map like the hardware on paper?
Oh, so basically, how can you map to a cell library, right? Is that what you're asking? You need to know what's in the cell library.
Yeah, but I want to know how the FPGA is, what it's built on.
Oh, okay, yeah. That's where the tools abstract the FPGA from you. So you may not know exactly what's going on if in the FPGA. The tools automatically map it to the FPGA. But I understand your concern, basically. You don't know exactly how the underlying FPGA is built. and you want to optimize things, and you don't trust the tool, then yeah, you cannot do much over there. You have to trust the tool over there. So basically, I think what you're getting at is, what if our substrate is really not available to us, right? And in many modern FPGAs, that's the case. You have to really find out what's going on underneath somehow. Sorry, I don't have a very satisfying answer to that. But that's a real problem, actually. A real problem people may be having also. If you want to specify a complex circuit and build on FPGA, you may not like what you want because the tool may not be doing something optimal. Okay, so let's stop here. We'll be back at the bell, and we're going to talk more about Verilog and hardware description. Okay, so this is what we have seen so far today. Hopefully it's relatively easy, and you will again see all of this in your labs firsthand, let's say. But there's more to Verilog basically, or there's more to hardware description, and right now we're going to get into that more. So you can actually write Verilog in many different ways, and let's see how we can express the same functionality by developing Verilog code. And we're still looking at very simple code actually. But before we go into that, you can write things at a low level of abstraction, which usually leads to poor readability. It's hard to read, for example, gates. If somebody throws you a gate level Verilog, if you don't, for example, do very nice modularization, then it leads to poor readability. But it may lead to, like, if you actually do a very nice, if you're actually at a very low level, it can enable the synthesis tools to do more optimization because they can actually map it better to the underlying libraries, and also do optimization on the equations, for example, that they may see. But if you write at a high level abstraction, if their abstraction level is very high, this usually leads to better readability, but it may actually lead to better, not so good mapping into the cell level libraries, that a mapping that doesn't satisfy your requirements, for example. This is something we discussed earlier also. That's the trade-off between these two levels of abstraction. So unfortunately, there's no best way of writing Verilog in the end. If it's readable and if it's optimizable, that's great, of course. There's some sweet spot, but it may not be easy to reach that sweet spot. So what we're going to look at is really equality checking, comparing two numbers. We've seen this as combinational logic in lecture 5. But let's take a look at it in Verilog. So you can define your own gates as new modules, clearly. And we will use an example of building a comparator or equality checker using our own gates, not the gates that are provided by Verilog, just to demonstrate that you can actually write very unreadable code. So this is an XNOR gate. You can actually specify this as my XNOR, behavioral, as you can see, bitwise operations, XOR, and then a NOT. And that's Z. Hopefully this is obvious by now. And an AND gate is even simpler because you use just a bitwise AND operation over here. So we're going to use this my XNOR and my AND to build an equality checker. And this is the gate level implementation. It looks terrible. All right. So these are two inputs, say, two input XNOR and two input AND gates. So basically, you have how many inputs over here? Basically, we said 4 bits, right? So A is 4 bits, B is 4 bits. Here, we didn't do a good job in specifying the A and B in a nice way also. As you can see, we're having individual bit inputs. And then output is whether or not they're equal. So first thing you do is 2-bit XNORs of each corresponding bits of A and B. And then you have a tree of AND gates on the outputs. Hopefully this is simple, right? And then the equal signal is tied to the output of the last AND gate. Okay? So recall equality checker. This is what we're doing. So the circuit you've seen earlier is similar to this over here, except this AND gate, this 4-input AND gate is 3 2-input AND gates, if you remember. So basically what we've done over here is, okay, can you go back? We can go back. We've used our descriptions of the XNOR and AND gates to build something that looks exactly like this. But again, this is terrible code. You can fix it by trying to do this, basically. You can do a sign. Basically, you can make things more, let's say, behavioral by getting rid of what you have, getting rid of your own code, let's say. This is an AND, this is an AND, this is an AND, and you do assignments. And then you can actually use Verilog's, let's say, powers to do a four input logical AND, bitwise AND. And this is short format, basically, in the end. So these are the outputs of the XNOR gates, and you basically take an AND of them. If all of them are equal, if all of the outputs are 1, then equal is assigned 1. Okay, so we kind of fixed that part. Let's fix this part also. Well, you don't need all of these my XNOR gates. You basically can express everything using the behavioral equations, right? So this is an XNOR, basically. That sounds good, right? But it's still not the best. This is actually an even better way of writing this equality checker, potentially, right? If A is equal to B, the output is 1, otherwise it's 0. This is very abstract, clearly. Again, we don't have gates over here. We have very abstract constructs in behavioral Verilog. Okay, so clearly this is more reusable and easier to read. A higher level of abstraction. That's the whole point over here. Okay, so let's assume that you have a module that can compare 4-bit numbers. What if in the overall design you need to compare 5-bit numbers or 6-bit numbers or 7-bit numbers or n-bit numbers, right? Can you parameterize this? Clearly, writing code for each of these is tedious and it's not fun. It's not nice. So we can have parameter modules. This is, again, hopefully obvious and simple. You can define module parameters, as you can see. For example, this mux2 is a 2-input mux, and the inputs can be of width, and the default value is 8. But by changing that default value, when you instantiate this mux, you can actually instantiate any n-bit two-input mux. Right? Makes sense, hopefully, right? So these are the 2 inputs, data 0 and data 1. They're of width wide. And width is specified when you instantiate it. If you don't specify the width when you instantiate this mux, the width is assumed to be 8 bits. Okay, and this is how you declare it, basically. Anytime you see you have a value that's a function of width, you use this expression. Okay, I think I already said this, but let's take a look at an example. How do you instantiate a parameterized module? This is our module that we saw earlier. As expected, this is basically, if you don't use any parameter, then the default is assumed. This is how you instantiate a 12-bit 2-input mux. And this is how you instantiate a 12-bit 2-input mux in a more verbose version. Basically, clearly this is a shortcut, and we've kind of used shortcuts over here. Assume the wire input and output ordering, and obey that ordering. Here, you can basically specify the width directly, as well as the inputs and outputs, and you can reorder them if you want, because you're clearly specifying explicitly what wires or what values and parameters and wires should be connected to the inputs and outputs. Okay, so hopefully this is simple again. What about timing? So tomorrow we're going to be concerned a lot about timing. This is going to be more interesting tomorrow. It's possible to define timing relations in Verilog also for simulation purposes, but they're only for simulation purposes. They don't dictate how long a circuit will take, because Verilog has no idea. Verilog is a description of the circuit. In the end, the hardware that you realize will dictate the timing. This is for you to verify the timing. And these timings cannot be synthesized also. They're used for modeling delays in a circuit so that you can make sense of the circuit in a timing way. So let's take a look at this. So here, for example, you define some time scale, and then a multiple of those time scales. Here, for example, you're assigning Z1 to A bar, and this takes effect after 5 time scales. And the second thing takes effect after 9 time scales. And you basically use this, hard code these. It's kind of cumbersome, I agree with that. But you can hard code these, and you can see this in a timing simulation, what happens. Basically, we were kind of assuming that it takes 5 time scales to do this knot, and it takes 4 more time scales to do this assignment for wire delay, whatever. And then you can actually combine this with multiple modules and multiple circuits and see the simulation and see what happens. You can see all of these timing delays in simulation. But now we're explicitly inserting them. So more on this later. Actually, this should be tomorrow, not later, today, because we're not going to talk about timing much today. Tomorrow is all about timing and verification. Okay, so some good practices. It's always good to be consistent in terms of essentially everything. Naming style, ordering of variables, etc. MSB to LSB ordering for buses, for example, most significant to least significant bits. This is better than this in general. Define one module per file. This is usually good, makes managing your design hierarchy easier. Again, these are not extremely strict guidelines clearly, but these are good practices. Use a file name that matches your module name. That helps. And always keep in mind that Verilog describes hardware. If you forget everything, keep this in mind, and your design will still be hopefully good, but your code may not be very readable. Just to summarize, so far we've looked at combination logic actually. I've not explicitly said this, but now we're going to jump into sequential logic also. We've been looking at hardware description for combination logic, and we've seen an overview of Verilog and studied combinational constructs. Let's take a look at sequential logic. But before that, any questions so far? Is this all easy, obvious? Okay. Yes, please, one. Yeah, I don't know automatically. I mean, there might be some tools that are designed that can potentially do that, certainly, because in the end, it's all software manipulation, right? But I don't think the tools that you're using in your lab support that. That requires your cell library to specify the timings and the tool to actually take those timings from your cell library. So it's certainly possible to do it, but I don't know if the tools do it. Do you know what the work? Okay, yeah, maybe you can figure out. But I think certainly it's possible, and I know some companies actually use that to actually optimize their designs. Very good question. What else? Anything else? Okay, so let's now jump into describing sequential logic, because clearly you cannot build systems without sequential logic, and sequential logic is certainly interesting, right? And Verilog provides specialized way of specifying sequential logic also. So, okay, what is sequential logic? Just to jog your memory, you have some combinational circuit that evaluates the outputs as well as the next state. And then you have a storage element that stores the state, potentially the outputs as well. And then you use that, you remember that information about what you have computed in the past to determine something in the future also. So that's your sequential circuit basically. It's a combination of storage elements and combination circuit, and we covered this in detail in last lecture, lecture 6. Now we're going to build this in Verilog. So basically, in Verilog, you can define blocks that have memory, flip-flops, latches, and finite state machines, clearly. And that's what we want to build using sequential logic. And sequential logic, remember from last lecture, whenever we want to transition state, whenever we want to change the value of the storage element, which is really the state of the system, that transition is triggered by a clock signal, right? That's what we said we're going to assume in the rest of this course. There's synchronous state transitions. We're going to assume synchronous logic in the end, or synchronous design. As we discussed, latches are sensitive to the level of the signal. Remember the D latch, and flip-flops are sensitive to the transitioning of the signal. So at the rising edge of the clock, the flip-flop captured the value, and that value stayed exactly the same for the entire clock cycle. And the next clock cycle, the flip-flop again captures the value in its input, just when the clock rises, right? Rising edge of the clock. And we described why this was necessary, right, for building finite state machines, because you need to have the entire clock cycle available for the state, because that state, that value, is used in the combinational circuit over here. So as you can see over here, the value of the state is used in the combinational circuit along with the inputs. And the combinational circuit design assumes that the clock cycle is long enough such that the function that you implement in the combinational circuit finishes within that time before the next state is captured in the storage element. Hopefully that makes sense. This is just summary of, let's say, part of the last lecture. We're going to talk about the timing later on tomorrow. But if you think about this, combinational logic constructs that we have seen so far in Verilog are not really enough to express this sort of sequential logic. And we're going to see new constructs that will enable us to express them. And these new constructs are going to be mainly two things: always blocks and this pause edge, neg edge, let's say, specifications of a signal. And you can guess what pause edge, neg edge is. Positive edge and negative edge of a signal. You can start reacting. Always is kind of, let's say, less intuitive. But we will see how it works. Okay, so this is the always block, basically. It's interesting because we're going to introduce it to implement sequential logic, but you can implement any logic in it. You can actually implement combination logic as well. But the main purpose of introduction is really for sequential logic. It can ease some of the combination logic implementations as well, or descriptions, I should say descriptions. We're going to describe combination logic as well using always block. And you will see why, because some combination logic is not easy, for example, to describe, or it becomes very cumbersome to describe without an always block like this. But basically, always block looks like this. You have always at some sensitivity list, there's some statement or a bunch of statements. There could be a begin and end, and there could be multiple statements. And the idea is whenever the event in the sensitivity list occurs, for example, whenever some change happens in a signal, clock, for example, then the statement is executed. That's it. If it's multiple statements, then all of those multiple statements are executed in some particular fashion, as we will see also. That particular fashion depends on how the statements are written as well. Okay, so that's what we specify. This says nothing about combinational or sequential, right? That's why always blocks actually can be combinational or sequential in the end, and we will do some exercise about that. Okay, so let's implement a D flip-flop using this always block. It's going to be very easy, actually. But remember the D flip-flop? It has two properties. Well, yeah, maybe this is the low-level implementation of the D flip-flop, but state changes on the clock edge. In this particular case, in the rising edge of the clock, when the clock goes from 0 to 1, a Q value gets assigned to D, essentially. And the data is available for the full clock cycle. These are the two properties that we desired and that we created when we actually created the D flip-flop, that we satisfied when we created the D flip-flop. I'm going to abstract this. This can be implemented actually in multiple different ways. This could be XNOR gates. Your book implements it using the XNOR gates. It could be something else also internally, as long as you satisfy these two properties. These two properties are really the higher level abstract functional specification, right? And we're going to look at it as a module that looks like this. Ignore the Q bar. We're not going to use Q bar, but Q bar is really easy to get clearly from this. Basically, Q gets assigned D when the clock goes from 0 to 1. Otherwise, Q remains unchanged. That's the idea. That's our abstract level. So in behavioral Verilog, well, clearly we can use D flip-flops to implement the state register in a finite state machine. These are all old information. And this is the description of a clock, no, not a clock, a D flip-flop in behavioral Verilog. This is not gate level, clearly. There are no gates here. I've introduced multiple things. It's called flop in this case. You can see it's a 4-input and 4-bit, and it's a 4-bit D flip-flop, basically. So what we've done over here is always at the positive edge of clock, Q gets assigned D. That's it. And you can see that there's a special thing called clock. That's the input. Post edge defines a rising edge, transition from 0 to 1. This is, again, part of the language. And statement is executed when the clock signal rises. Remember the always block? This statement is executed when something happens to the signal, and something is positive edge of the clock. Make sense? This could have been the negative edge also. Then it's going to be a negative edge triggered flip-flop. But we said we want positive edge. Okay. And once the clock signal rises, effectively, the value of D gets copied into Q. Make sense? So Q gets the output. Q is assigned D, in other words. And there's something else that we will see. Output, if it's a sequential output like this, it needs to be defined as register or reg in this case. This is an unfortunate terminology maybe, but it's really not to be confused with a register. This is just something that gets assigned in an always block in a sequential way. Make sense? Okay, so you will get used to the syntax. Syntax is not the best, but you can see that how simple this is, right? This is really specifying sequential logic or the D flip-flop without going into any low-level details. Now you can take this, synthesize it, and based on your underlying cell library, you may get potentially this or something else. Again, it could be XNOR gates. It could be something else, right? Okay, so let's take a look at this a little bit more. What does this mean? So basically, within an always block, we don't use assign statements because these are potentially stateful. We use the special assignment. It's called a non-blocking assignment. Non-blocking assignment means that this doesn't block whatever happens in the next assignment. We'll see a better description of this soon. For now, ignore that. Assume that you have a non-blocking assignment over here. And you need to, the variables that are assigned inside the always block need to be declared as regs. Again, this is a Verilog rule. I didn't make up the rules, people who designed it. The name reg doesn't necessarily mean that the values are registered. It could be, but it doesn't have to be basically, because this could be a combinational thing as well, as we discussed. So we'll see examples later that where reg actually can be combinational. Okay, so before we go into a little bit more about blocking, non-blocking, let's take a look at some things that you may need for your labs also. This asynchronous and synchronous reset, or at least good to know. So reset signals. Reset is very important. Remember, we discussed finite state machines. You need to reset the finite state machine to a known state before you start operating. Whenever this computer starts, it has to start at a known state. So there's a reset signal that goes and sets the finite state machine to a known state that the designer of the computer said, this is the state that should start in, otherwise it won't work, right? Initialize everything to something that is supposed to be, the values that they're supposed to take initially. Okay, so I kind of said this. For this, you need a reset signal. Right? Usually, this reset signal is activated at system start on power up, but there could be other cases also potentially. And there are two ways of designing the reset signal. One is asynchronous to the clock, and the second is synchronous to the clock. This is very similar to synchronous versus asynchronous design principles that we discussed earlier. So asynchronous says reset happens whenever it happens. It's independent of the clock, basically. Whenever the reset signal comes or goes down, negative edge or positive edge, the computer resets, or you go to that state, reset state. In this case, reset gets the highest priority, clearly. This may be sensitive to glitches, may have metastability issues, as we will see tomorrow a little bit in tomorrow's lecture, basically. But asynchronous reset is also used in systems because it happens very infrequently, basically. So synchronous reset, on the other hand, is dependent on the clock. It's the reset signal, whether or not you actually take the reset signal, reset the finite state machine, or reset the flip-flop, is sampled with respect to the clock. If the clock is going from positive edge and the reset is low or high, then you take the reset signal. Right? If the reset signal changes when the clock is not in an appropriate value, then it doesn't matter. The computer doesn't reset. So the reset should be active long enough to get sampled at the clock edge, basically, in this particular case. Now you can see why asynchronous reset also kind of makes sense, right? Well, for example, I'm a user. I want to reset the computer. I press a button, and it's independent of the clock in a sense, right? Make sense? So you need some asynchrony to make sure that that reset button actually works in a computer, because the clock may not go from the rising edge to low. The clock may not take the rising edge or go from 0 to 1 when I'm pressing the button, right? I may not be able to capture that point in time. I need to press the button long enough to potentially capture that point, right? Okay, that's just for you to think about. There needs to be, whenever you have interaction with the real world as a computer, then the computer needs to have some sort of asynchrony, because real world is asynchronous. We're not operating based on a clock over here, right? We're doing operations completely asynchronously to a notion of clock. As a result, when you're interacting with a computer that's synchronous, and that's true for all of nature, actually. When the nature is interacting with a computer, that's completely asynchronous. When you're receiving signals from the outside, for example, that's completely asynchronous. The outside signals have no knowledge of the clock. So if you assume that the outside signals need to be sampled at the time the clock changes, then you may be missing some of those signals. You really need to add some asynchrony to the circuit. And that's important to think about. So there's some domain that needs to transition from asynchronous to synchronous if your computer is completely synchronous. Okay, so if you actually have synchronous reset, this results in a complete asynchronous circuit. So this is just to jog your memory. We talked about this actually in the last lecture, asynchronous versus synchronous state changes. What we have described is one example of it. So remember, an asynchronous machine, state transitions occur when they occur. It's a generalization of the asynchronous reset in a sense. But most computers are synchronous machines. State transitions take place after fixed units of time, dictated by a clock. And we assume synchronous systems in most of this course, but this was one example where asynchronous makes a lot of sense, actually. Whenever you're interacting with humans or nature, they're not operating based on the clock that the computer is operating on. Okay, so let's take a look at how this D flip-flop with asynchronous reset is implemented. So you can have a D flip-flop with asynchronous reset, as you can see, and this is how it's implemented here. Let's take a look. So basically, two events, because of this always statement, two events can trigger the process. Process meaning the this block over here, always block over here. Statements execute when two events happen, or any of the two events happen. When the clock goes from falling edge to rising edge, when the reset signal goes from, when the clock goes from 0 to 1, that's the positive edge. That's also called the rising edge of the clock. And when the reset signal goes from 1 to 0, that's called the negative edge or falling edge. So I'm just giving you another terminology over here. Pos edge means rising edge, neg edge means falling edge also. The rising is 0 to 1, falling is 1 to 0. Any of these two events can trigger this assignment over here, these two assignments, potential assignments, I should say. So let's take a look at what happens. So clearly I've used begin and end here, as I mentioned earlier. For longer statements under an always block, you use begin and end. In this example, it's not necessary, but a good idea in general. So here, let's take a look at what happens. If reset is equal to 0, then the output of the flip-flop gets 0, regardless of the clock. So you first check the reset. Is reset 0? Q is set to 0. Because when reset goes from 1 to 0, independently of the clock, the statement gets executed. Right? You can convince yourself of that. And that's why this is asynchronous. Because reset can happen independently of the clock on the negative edge of the reset signal. This statement gets executed, and the flip-flop gets reset. If there's no reset, meaning if reset is not 0, then the regular assignment takes effect. If reset signal is not 0, that means you're executing the statement in the positive edge of the clock. So you're operating just like a regular D flip-flop without any reset that we have seen so far. Does this make sense? So now we have two signals that are triggering state transitions in a D flip-flop. One is to reset it. The other is to do the state changes whenever reset is not happening. Okay? Okay, this is a D flip-flop with a synchronous reset. The difference? Well, okay, the difference you can basically, I don't know what's happening here. You can basically look at the difference, right? It's very similar, except the synchronous reset doesn't have the sensitivity. It doesn't have the reset in the sensitivity list. Only at positive edge of the clock you react, or these statements get executed. And if reset is 0 at that point in time, good, you reset the flip-flop. Otherwise, you basically change the state to the input value. This is the difference between synchronous and asynchronous. As you can see, reset happens only when the clock rises. Okay, there are many different types of flip-flops. Very quickly, we also had an enable signal. This is an asynchronous D flip-flop with an enable signal also. So you can basically make things more complicated. What is an enable signal? Enable signal says if the flip-flop is not enabled, then you're not going to sample the input value and propagate it to the output value. Only if it's enabled, you do it. And you can see this statement, this behavioral statement again, satisfy that. If reset takes priority, so you again sample, you execute these statements on the positive edge of clock or negative edge of reset. Reset takes priority. Otherwise, if the enable signal is 1, then you sample, then you basically propagate the input value to the Q output. Okay, so in this case, enable signal is not in the sensitivity list because it really doesn't trigger state change by itself, right? State change happens either on reset signal falling or clock rising. So there's no reason for the enable signal to be in the sensitivity list over here. In fact, if you put it in the sensitivity list, you're making a mistake. Why? This always statement gets executed when the enable signal changes, let's say positive edge. And when that changes, you will basically propagate the propagate D to Q, which means that you're violating our principle of D flip-flop, which is the state should not change during a clock cycle. You're really changing the state based on an enable signal that is independent, asynchronous to the clock. Okay, so keep that in mind. So whenever you're doing synchronous designs, you should be very careful what you put over here into the sensitivity list. Okay. Okay, I think I already this. You can read this as Q gets D only when clock is running and enable is 1. So contrast this with a D latch. So you can also have D latches or latches in Verilog, and this is one way of describing the D latch. Again, it's very simple. Sensitivity list is clock as well as the D value. If clock is high, Q gets the value of D. That's it. So remember, latches are level sensitive. In this case, we have a level 1 sensitive latch, meaning if the clock is high, output should get the value of input. And this is essentially specifying that. And you can convince yourself again, it's a transparent latch. Any questions? Okay, I go through this quickly because we covered latches and flip-flops, and these are relatively easy to understand. Once you actually start writing, it'll be even easier to understand. But this is our summary of sequential statements so far. So sequential statements are always within an always block. That's kind of interesting, always within an always block. The sequential block is triggered with a change in the sensitivity list, don't forget that. And signals assigned within an always must be declared as reg. And you use this less than or equal to sign for non-blocking assignments and do not use a sign within the always block. We will see non-blocking versus blocking next. And a sign is really for wires, essentially, not for always statements. Okay, let's take a look at this, some more basics of always blocks. So you can have as many always blocks as needed. So for example, and this now shows you the concurrency of the hardware. So you can see always at positive edge of clock, you have this special gets the D value. Always at, you could also do negative edge clock here, it doesn't matter. Q gets normal. And then here, normal gets assigned to special bar over here. This is a simple assignment. And all of these operate concurrently, actually. And we will see that concurrency when you actually do this. So of course, one thing that is not allowed is the assignment to the same signal in diff blocks. So if you assign special here, you cannot assign special here as well. Why? Because that makes no sense, right? Now, you have multiple things that operate concurrently, and you're really overloading a value, an output value, essentially a value over here that you are changing in this particular case synchronously. And it doesn't make sense because you don't have any idea which one is correct, right? That's completely incorrect or inconsistent. Okay, there are other things over here. There's wire and reg. You can see you can have regs internally also. They don't have to be just outputs. But if you want to declare some variables that are assigned inside the always blocks, you need to declare them as regs. They cannot be wires. Of course, other things that are assigned outside of the always blocks should be declared as wires. Okay, so why does this always block remember? Meaning that's the basic of sequential circuits. Why does it remember? So basically, the statement that you have in the always block describes what happens to signal Q, right? You should always ask the question, what happens when the clock is not rising? So this statement gets executed when the clock is rising at the positive edge of clock. So what happens when the clock is not rising? Well, that's the assumption we have in the D flip-flop. The value of Q, the old value of Q is preserved, basically. You remember what the old value of Q was, whatever was captured in the prior time you updated Q. That's why this remembers, basically. It gives you, the specification here says Q is updated at the positive edge clock, but it doesn't say anything about what happens in all other cases. And the assumption is that the output value gets preserved with the prior value of the output since the prior update. Okay? Now that's interesting because what if you actually specified that value to not get preserved? Now that brings us to always blocks that are combinational and not sequential. So if by looking at this is definitely sequential, right? Because you remember a value, even though you didn't explicitly assign it. We explicitly assigned it at some point in the past, of course, but you don't explicitly say you remember it, right? There's no explicit specification here that says you remembered an old value. It's just how it is. But you can always write, you can also write always blocks that are combinational, as I said. And if you look at this is purely combinational. There's no remembrance. What does that mean? Basically, you always specify a state change in this particular case whenever an input changes. Okay, that's the idea. So result is reg, declared as a reg, as you can see. We have in INV and data. And these are the two inputs to the circuit, INV and data, you can see. And whenever INV or data changes, the result gets assigned a value. If INV is true, result gets the inverted data. Otherwise, result gets data. Now, by looking at this, you can say this is combinational. Why? Well, first of all, I've already described this, but this is combinational. It has no memory because result is assigned a value whenever an input value changes, and we have two input values, inval data, and in all cases of the if and else block. So there's no condition under which result does not get assigned a value. meaning this is combinational, because there's nothing to remember here because you didn't omit something. Okay, so it's kind of odd in the sense that this always block remembers when you omit something, right? But when you don't omit something, it doesn't remember. That's the key distinction. And I've already summarized what does it mean to not omit something. Whenever the output, all outputs are assigned a value whenever an input value changes, any input value changes, and in all cases of if and else statements. If you have if and else statements over there in the always block. Okay, so now this is the combination. Now what you can do with this always block became a little bit powerful. You can specify combinational circuits that are, let's say, much more complex. You can have if, else, case statements, as we will see. So basically, it's more powerful. It's also kind of odd because now you can specify both sequential and combinational logic, and you remember something if you omit something. So, okay, to repeat myself, an always block defines combinational logic if all outputs are always continuously updated, meaning all right-hand side signals are in the sensitivity list, meaning inputs are in the sensitivity list. You can always use always at star, asterisk for short. Basically, any input triggers the execution of the statements in the always block in this particular, when you do this particular thing. And all left-hand side signals, meaning outputs, get assigned in every possible condition of if, else, and case blocks. Okay, I think you've seen an example of this. It's easy to make mistakes and unintentionally describe memorizing elements. So if you want to use always blocks to do combinational circuits, to describe combinational circuits, it's easy to make mistakes because you may omit something, basically. Whenever you omit something, meaning whenever 1 and 2 doesn't get satisfied, you may have a latch or a flip-flop, some sequential logic, basically. And in this case, you're basically at the mercy of the tools. Tools may warn you. Yeah, check the warning messages, basically. Warning messages are there for a reason. But always block allow powerful combinational logic statement using if, else, and case. So let's take a look at some examples. Are these sequential and combinational? Maybe I'll ask you. Is this sequential or combinational? Anybody quick enough to look at this code? This is the always block, as you can see. There are two outputs, out A and out B. Anyone? Yes? You say combinational. Any other takers? Yes? Why? Exactly, yes. That's the reason, basically. Well, it should be out B, actually. I don't know why this covers out A. I'm going to fix this. Sorry. So you're more correct than the slide, as you can see, because out A is assigned regardless, right? Okay, so that's the reason, basically. Out B is assigned only if enable is true, even though the sensitivity list contains any signal, basically. Out B is not assigned when enable is not true, meaning that you preserve the old value out B inside out B. Okay, so it's easy to make mistakes, basically, especially when you're starting. The second one, is this combinational or sequential? Any takers? Yes. Exactly, yes. Yeah, this is sequential because this doesn't get executed when enable changes, right? Yeah, basically every input signal should be in the sensitivity list. Okay, very good. So you can actually have fun with this, and we actually asked some questions in the exam also related to this sort of relatively easy things, but this tests basically whether you've kind of done the labs in a sense. Okay, always block is not always practical or nice. For example, both of these statements are describing a multiplexer. This is an always block-based multiplexer. This is a much simpler multiplexer, clearly. Hopefully people agree that always block is kind of, it is correct, it works, but it's very cumbersome, right? I would use a multiplexer that looks like this. So for simple things, always block may not work very well. But for more sophisticated things where you have a lot of cases, for example, always block may be a lot easier, right? So in this case, you can see that this is a combinational thing. Based on the data, you assign the output segments, and there may be many different assignments that you come up with. And default is segments is assigned to 0. This ensures that in all possible cases, segments is assigned based on this default, because you may not declare, based on the value of the data, you may not actually declare all possible values of the data in the left-hand side over here, and then you default to default case. So this is again combinational, and this is a case statement, as you can see. Based on the value of the data, you do an assignment to segments. And then clearly, you can add more inputs over here, right? Some other logical statements, but we keep it simple over here. So summary, always block, if else can only be used in always blocks. That's a restriction of the language. And the always block is combinational, as we discussed. Well, if all of the registers with regs within a block are always assigned to a signal, and if you actually want to make sure that's the case, use the default case. So if you use a case statement and a default case, you make sure of that. Of course, that may not be correct, but you still need to make it correct. Okay. Basically, case X statement actually is used for checking don't cares, but I don't have an example of that right now. So let's go to non-blocking and blocking assignments, because it's going to be important. So these assignments are non-blocking. So what does this mean? All assignments are made at the end of the block. So A gets value 1, B gets value of A. The value B gets is not dependent on the previous statement. Make sense? So that's where Verilog differs from a normal sequential programming language. It really models this state not changing until the end of the clock cycle, right? So A gets this value, B gets the old value of A, in a sense, what was there before in the block. Hopefully this makes sense, right? We'll see the difference between equals and this less than equal. All assignments are made in parallel. Process flow is not blocked. That's why this, basically, you can think of this as logic executed completely in parallel, right? This A gets assigned this whatever equation is over here, concurrently with what B gets assigned, whatever is equation over here. That's the beautiful concurrency in hardware. That's essentially what you get in combinational logic in hardware. Okay, but I mean, you can also express blocking statements, which basically operate more like similar to a sequential language. Here, A gets assigned value of 1 immediately, and the second statement is dependent on, assumes that the first statement is executed. Okay, this is more like an existing software programming language. So process waits until the first assignment is complete. It blocks progress. And this is similar to sequential programs, and there's a good reason to also potentially do this, because you may be actually describing a hardware combinational circuit where the circuit looks like that, right? B gets assigned value A after A gets assigned some value, right? It certainly makes sense. But this serves a different purpose. This serves the purpose of really sequential logic, where state changes at the end of a clock cycle, or at the end of a signal, let's say, based on the sensitivity list. Does this make sense? This is an important distinction, basically, between non-blocking and blocking assignments. So why do you use non-blocking statements? Because non-blocking statements allow operating on old values, enable easy sequential logic descriptions. Hopefully, I've convinced you of that. Blocking statements allow a sequence of operations, meaning they allow operating on immediately updated values. It's more like a software programming language that's sequential. And if the sensitivity list is correct, actually blocks with non-blocking statements will always evaluate to the same result. And this, you need to think about this a little bit. But let's take a look at a blocking assignment over here. This is actually a carry, it's a full adder basically with carry and propagate circuit. Always, you can see it's combinational actually if you study it. Assume that P gets 0, then D gets 0 also. Now the value of P that's used over here is the result of this. And the value of P that's used over here is the result of this. And the value of G that's used over here is the result of that statement. So for example, if A changes to 1, all values are updated in order. If A changes to 1, P changes to 1, G changes to 0, S changes to 1 based on P, and C out actually changes, kept as 0 because both G and P actually change. The same example, if you do non-blocking assignments, if A changes to 1, all assignments happen concurrently, meaning when S is being assigned, P is still a 0. So the new value of P doesn't affect the new value of S. Everything gets assigned at the end of the, let's say, if this was clocked, for example, at the end of the clock cycle. Okay, so this model is actually a different circuit, as you can see. Okay, something is happening. Basically, you can see that the result here is 1000, whereas the result here was 1010. So it's best for you to actually go over this and figure out how this works. Okay, the same example. So basically, this is the same example, non-blocking, and P changes, then you basically get a different result. Okay, this is a great place to stop. We will continue tomorrow.